Welcome to this second video of a playlist about the preparation of fluoroalkylarenes. This video is about the fluoroalkylation of aryl halides and esters, either directly or by intermediate formation of a methylated arene, for instance a Grignard reagent. I have discussed the general properties of fluorinated organic compounds in part 1 of this video playlist. The specific examples are organized according to the starting material in the order given here. We'll start with aryl halides and diazonium salts, followed by aryl esters, benzoic acid derivatives, aryl sulfones and sulfonium salts, and finally with some examples of the fluoroalkylation of arines. Aryl iodines are reactive but relatively expensive and are only rarely used for large-scale preparations. Most reported examples of the fluoroalkylation of aryl iodines are copper-catalyzed and probably involve trifluoromethylcopper and aryl copper intermediates. In this example, catalytic copper and a trifluoromethylsilane were used as reagents. No displacement of bromide occurred. Interestingly, chlorodifluoroacetates can also serve as a source of trifluoromethylcopper by intermediate formation of difluorocarbene. Here, an iodinated nicotinic ester reacted with an excess of methylchlorodifluoroacetate to a trifluoromethyl nicotinate. Side reactions were displacement of chloride from the pyridine ring and the oligomerization of difluorocarbene to longer perfluoroalkyl chains. These longer perfluoroalkyl groups were formed when too little copper was present.
Alternatively, silyl esters of chlorodifluoroacetic acid can also be used as a difluorocarbene source. Here, iodide was again displaced faster than bromide. Trifluoromethylcopper has also been generated in situ from chlorodifluoromethane and copper tetrafluoroborate as shown here. Despite the huge excess of reagents, no further fluoroalkylation or reduction of the product occurred. Under more vigorous conditions, trifluoromethylcopper can also be generated from trifluoroacetates. Here, an iodo-naphthalene was heated with potassium trifluoroacetate and copper iodide to 150 degrees Celsius for 2 hours, and a quantitative yield of the target product was obtained. Another potential source of trifluoromethylcopper is fluoroform. Treatment of a mixture of copper chloride and potassium terbutoxide with fluoroform and then with an aryl iodide gave a high yield of trifluoromethylarene. In this example, trifluoromethylcopper was generated from copper bromide and a trifluoromethylsilane. Addition of hexaiodobenzene then gave a mixture of mainly 3 products: hexatrifluoromethylbenzene, a phenol, and a reduced product. The phenol was probably formed by aromatic nucleophilic substitution with the solvent, followed by hydrolysis, and the reduced product by nucleophilic attack of trifluoromethylcopper or any other nucleophile at iodine. Polyhalogenated arenes are quite acidic and their anions therefore good leaving groups. Trifluoromethylsulfonium ylides are another alternative source of trifluoromethyl groups. As in the previous examples, the reaction here was conducted in a polar aprotic solvent, DMF in this case, which are good at dissolving salts and at stabilizing reactive intermediates.
In this example, catalytic copper and a trifluoromethyl borate brought about trifluoromethylation of 4-iodoanisole. The borate was prepared from a trifluoromethylsilane and trimethylborate. Iodinated heterocycles, for instance pyridines or indoles, can also be trifluoromethylated as shown here. No protection was required and no trifluoromethylation at nitrogen occurred. In this example, first a difluoroaryl acetic ester was prepared by reaction of an iodide with a silane, and after saponification the acid was decarboxylated. As discussed in the first video of this playlist, fluoroacetic acids do not decarboxylate readily, and heating to 170 degrees Celsius for 2 hours was required in this instance.
Aryl bromides are almost as reactive as aryl iodides, but less expensive and therefore usually preferred as starting materials. Here, an aryl bromide was first converted into a Grignard reagent and then alkylated with difluoroiodomethane. Because fluoroalkyl iodides are poor electrophiles, the reaction was catalyzed by nickel and preceded by an intermediate difluoromethyl nickel complex.
This same reaction can also be catalyzed by iron complexes. Instead of difluoroiodomethane, difluoromethyl sulfones can also be used as electrophiles, as shown here. The Grignard reagent was first transmetallated to zinc, and an iron catalyst was again required to enhance the reaction rate and selectivity. No displacement of fluoride from the pyridine ring occurred.
Bromide can also be displaced directly with trifluoromethyl copper. Here, dibromobenzoic acid was fluoroalkylated directly without any protection of the carboxyl group, and the orthobromine atom was displaced preferentially. As a byproduct, 10% of a phenol was formed.
In this example, a protected chelating 2-bromobenzoic acid was difluoromethylated with a silane and 10% of a copper-carbene complex. An alternative to difluoromethyl copper is DMPU-stabilized bis-difluoromethyl zinc. This reagent can be prepared from diethyl zinc and difluoroiodomethane. With the aid of a nickel catalyst, aerobromides were difluoromethylated by this reagent at room temperature in DMSO. Zinc waste is usually less expensive to dispose of than copper waste.
This here is a further variation on the same theme, with a special diamidine as ligand for nickel. Again, a 3-bromopyridine was difluoromethylated selectively, while the arioxy group in position 2 of the pyridine ring was not displaced. Aryl chlorides are quite unreactive, and only bulky, electron-rich palladium complexes are capable of cleaving the carbon-chlorine bond. Here, such a bulky catalyst was used to fluoroalkylate 4-chloroanisole with a difluoromethyl silane. In this example, a nickel dipyridyl complex combined with an excess of chlorodifluoromethane and zinc brought about a similar reaction as on the previous slide. The benzhydryl alcohol was neither reduced nor oxidized. Here, difluoroacetophenone was first arylated with chlorobenzene and a bulky palladium catalyst. Cleavage of the ketone with potassium hydroxide then gave difluoromethylbenzene in high yield, without any loss of fluorine atoms by nucleophilic defluorination.
Anilines are readily available and easy to convert into diazonium salts. These also react with most fluoroalkylating reagents. In this example, nitrosation and trifluoromethylation were realized in one step, with isoamyl nitrite and a trifluoromethyl sulfonium salt.
Diazonium tetrafluoroborates are relatively stable and safe to handle, and can be fluoroalkylated directly. With an excess of sodium trifluoromethane sulfonate and 2 equivalents of copper-1, the main product was the expected trifluoromethyl arene.
With catalytic copper, however, arylation at sulfur was faster than cleavage of the sulfur-carbon bond, and a high yield of trifluoromethyl sulfone resulted. Reaction of a diazonium tetrafluoroborate with stoichiometric bis-trifluoromethyl silver gave mainly a benzotrifluoride. The required reagent was prepared from fluoroform and silver triflate, as shown here. This is, of course, quite expensive, and few target products will be so valuable as to warrant this procedure. This here is a more cost-conscious strategy based on a fluoroalkyl silane and 1 equivalent of copper thiocyanate. Because of the high reactivity of diazonium salts, no heating was required. Aryl esters are unreactive and only rarely used as starting materials for aromatic nucleophilic substitutions. This here is again an expensive procedure requiring a slight excess of a nickel diphosphine complex. The intermediate aryl-nickel complex did not undergo reductive elimination spontaneously, but had to be oxidized with an excess of trichloroacetonitrile. Aryl palladium intermediates can be generated by strong heating of benzoyl palladium complexes. Temperatures above 150 degrees Celsius are often required to cleave off carbon monoxide, and this strategy has been used to convert benzoyl halides into aryl halides in the gas phase, with supported palladium as catalyst. When heating benzoyl fluorides with catalytic palladium and an excess of a trifluoromethyl silane, trifluoromethyl arenes can be obtained, as in this example. Benzoyl chlorides react similarly. With a bulky phosphine ligand, however, the decarbonylation already proceeded at room temperature, what greatly increased the scope of this chemistry. Occasionally, aryl sulfones can be suitable substrates for aromatic nucleophilic substitutions. Here, with the aid of a strong base, a difluoromethyl sulfone was arylated with a benzothiazolial sulfone. Then, one further cleavage of a carbon-sulfur bond with potassium hydroxide yielded difluoromethyl benzothiazole. Triaryl sulfonium salts can also undergo aromatic nucleophilic substitution with metallated fluoroalkyl groups. In this example, such a sulfonium salt was prepared from a sulfoxide, and treatment with bis-difluoromethyl zinc and catalytic palladium yielded the target difluoromethyl arene. Arynes are highly reactive, short-lived electrophiles that can also react with metallated fluoroalkanes. Here, an aryne was generated from an aryl triflate and then trapped with trifluoromethyl silver and an iodoalkyne as electrophilic iodinating reagent. A 2-iodobenzo trifluoride resulted in moderate yield. The required trifluoromethyl silver was prepared from a silane and silver fluoride in acetylnitrile. Trifluoromethyl copper reacts in a similar way as shown here. The aryl copper intermediate was further alylated with a substituted alyl bromide. So what about potential side reactions? I've already mentioned some along with the examples. If reducing agents are used to generate fluoroalkyl radicals, for instance metals or dithionite, these can also reduce the starting electrophile to an unsubstituted arene, as in this example, or generate aryl radicals and biaryls. Here are some more references which you can also find in the description of this video. You can find a PDF version of the slides and transcript under the Posts tab of my channel. The next video of this playlist is about the preparation of fluoroalkylarenes by ring-forming reactions, for instance cyclocondensations or cycloadditions. See you there.